Okay, hi. That took a little longer than I thought, but I think it's good to see these things again, especially after 2 weeks, basically, of not seeing you. Yeah, it's over 2 weeks now. So, okay, so now we get to the theorem in 9.5 called Rao-Blackwell. And let me just write it down in our language. We'll write it. So, theorem, let theta hat be an unbiased estimator for theta with a finite variance and let U be sufficient statistic for theta. Okay, then E of theta hat given U is equal to theta, and variance of E of theta hat given U is less than or equal to the variance of theta hat. Now, could you do the proof? Yes. Proof's not hard. Proof is just using each of the properties and for each result. So the first one results from property one. So the proof, maybe I should just write follows, because we did do it. Follows from property 1 and 2 above. It's straightforward. So again, I think this is good not to write everything down. We did this already. So the property here, I can show this. I can't help it. Okay, let me just, so the first one is E of this, E of theta hat given U. This is just equal to, from property 1, E of theta hat, which we said is an unbiased estimator. So this is equal to theta. So this tells me that this new, so let's write in words. So E theta hat given U is unbiased estimator of theta. Okay, and now for the second one, and since we can just use that second property, right? So we have variance. If I just manipulate the conditional variance property, this is equal to variance of theta hat minus the expected value of the variance of theta hat given U. Right, I just added this to this, I just subtracted this from this side. Okay, but this must be then less than or equal to the variance of theta hat, because variances are non-negative. Variance of theta hat given U is non-negative function of U. So E variance theta hat given U must be greater than or equal to 0. Okay. So what this says is, so in English, so starting with theta hat and U, E theta hat given U is possibly, maybe not, maybe it's the same, a better unbiased estimator for theta. Oh my God, I'm writing and you're not even. So starting with theta hat and U, E theta hat given U is possibly a better unbiased estimator for theta, right? Because it's also unbiased and the variance cannot be any worse. All right. Well, one thing you should check is that if if you have a function, of u and you take the expected value of it with respect to u, you just get that function back. In other words, if I said, what's e of g of x given x, your answer should be just g of x. You can check the mathematics of that. It's true. What that tells you is that once you take e of theta hat given u, you get a function of u, and that cannot be improved on. So that this theorem works to possibly improve theta hat once, but it can't be used iteratively to continuously get a better and better and better estimator. So let's write that down. So since E theta hat given u is a function of u is equal to h of u, and E h of u, so h of u will be unbiased and it will have at least as good a variance as theta hat, but I can't do it again. E h of u given u is still h of u. So this says, so this theorem can be, theorem can be applied once. If you apply it again, you're wasting your time. You're going to get the same thing back. All right. Now, one more twist, how this is used. Okay. So we have this thing called an MVUE, minimum variance unbiased estimator. So, from the above argument, we see if we find a sufficient statistic u for theta and g of u is unbiased for theta, then the above theorem does not improve g of u. Because for any sufficient statistic I put in there, E g of u, given any sufficient statistic, given u, or any other sufficient statistic, is still just equal to g of u. So we can call g of u a minimum variance unbiased estimator for theta. Now, there is one little caveat. If I started with a different u, if I start with one u as opposed to another, it is possible to get different g of u, and some may have lower variances than other. We're not going to make that distinction in our course. It's pretty subtle, and generally we can just say we're going to ignore that subtlety. Most of the time, that you get the way you find these sufficient statistics is through the factorization criteria, and it can be shown that those are the absolute minimum. Those actually lead to the true MVUE, the absolute minimum variance unbiased estimator. But we're going to leave that much alone, I think. Okay, so we're almost there. So I just want to do an example two examples for how to use this. Think we have time? Okay, yeah, already over 10 minutes. Let's do another video.